Let's study the mean value theorem of differential calculus. You know this theorem already. Here we have a function which is continuous and it's differentiable, so the derivative exists. Then we can represent this number as the derivative of the function at some point. So we have the graph of the function from one point to another point. We can draw the line connecting these points. The slope of this line will be the difference of the values of the function divided by the difference of the values of the variable. The equation of this line would be this one. On the other hand, we can draw some tangent lines on top of the graph of the function. If we choose the tangent line correctly, we can make it to be parallel to another line. The equation of the tangent would be this one. Because these two lines are parallel, their slopes must be equal, and therefore we have our equation. This is called the mean value theorem of differential calculus because in the claim we have a derivative. The mean value theorem of integral calculus is quite much similar. There we have a continuous function and we obtain this kind of equality for some value c. We can write the equation in a little bit different way. On the right we have the area which is below the graph of the function. The claim is that we can have a rectangle of the same area. If we choose our point C in a nice way, we can draw a rectangle. Now the area of the rectangle is the same as the area below the graph. If capital F is the integral function of small f, then we can write the integral as a difference of these values of capital F. So this mean value theorem is equivalent to the other one. There is also a similar theorem for continuous functions. It says that if we take a point from between the values of the functions, well, let's take here to be the value y, then we must have that the function obtains the value y for some point c. So if we draw here a line like this, and we start to go from the point FA upwards, we must at some point cross the line. We find some value c such that the value of f at c is equal to y. So our main topic has analogues for integrals and for continuous functions. The theorem has many applications. It allows us to prove the L'Hopital theorem. It gives us the Taylor polynomials or series, and it allows us to prove some inequalities. How do we obtain the Taylor polynomials or series? We can take our identity and we can write it in different way, and still in a different way. It shows that we can approximate the value of f at b by using the value of f at a and choosing the derivative here in a suitable way. So, if in the linear approximation we would change the derivative in a little bit different way. Oops, I had a mistake there. If we would change the derivative by changing the value of a to c, we would get the equality. In the same way, this second degree approximation can be made to be exact if we just change the derivative, the second derivative, to be evaluated in some different point. Analogously, we can make the nth polynomial approximation, it means the nth Taylor polynomial, we can make it to be exact if we add this kind of term here. Here Taylor's theorem has been written in a different way. Let's find the Taylor polynomial of order 4 for the function sine of x at 0, and let's estimate the error on this interval. So now our function is sine of x, and we need to have the derivatives of our function at 0. So let's make a table. Let's write here the number k, here the kth derivative of our function, and the value of the kth derivative at 0. If we have the 0th order derivative, it means that we take the function itself. So that's sine of x. And value of sine at 0 is 0. If we take the first derivative, derivative of sine will be cosine. Cosine at 0 is 1. The second derivative of our function is the derivative of cosine, that means minus sine of x, and the value of that at 0 is 0. Third derivative would be minus cosine, which gives minus 1. Fourth derivative would be sine of x, and our value is 0. So if we make a sequence where we gather all the values of the derivative at 0, we get that the values will be 0, 1, 0, minus 1, and then again it will be repeating. So how will be our absolute approximation? Sine of x is, we take the value of the function at 0, divide by this one, and we'll have this term to power 0. Then we will take the value of the derivative at 0, divide by the factorial of 1, like this. Like this. Here, this value seems to be equal to 0. This value is 1. So the second term gives us x. This derivative here seems to be again 0. The third derivative is minus 1. So this term here will give us minus x to power 3 divided by the factorial of 3. So that means minus x to power 3 divided by 6. Again, the next term will be 0. So this is all what we obtained, and for the error term we have the fifth derivative of our function will be equal to cosine of x, and we evaluate it at some point c. C is between 0 and x. So here is our Taylor polynomial for sine and the error term. If our variable x is on this interval, it means that our value c will be also in this interval. How large can our value be, the value of the error term? Well, absolute values of cosine are at most 1. And now because our x is like this, the absolute values of x to power 5 will be also less than 1. So we will have something which is less than 1 times 1 divided by the factorial of 5. It will give 1 divided by 120. Well, that's less than 0.01. So here is one approximation for the error. We studied the mean value theorem of differential calculus, and to this theorem we found, for example, this example, how to get Taylor polynomials.